So, obviously, our globe is not getting bigger. Essendites did discover that in certain places in the middle of oceans, new rocks are being created and creating a process called seafloor spreading. Well, if that was the case, you would think the globe would be getting bigger in size. So obviously, we figured out that somewhere else in the world, older rocks have to be getting destroyed, and therefore the Earth is staying the same size. So we have, to summarize, at ridges, we have seafloor spreading, which is a divergent plate boundary. And at trenches, we have ocean floor getting destroyed, okay, along subduction zones. So this is basically the big picture of where rocks are getting formed, where rocks are getting destroyed, and why the Earth is staying the same size. It is not possible for ocean crust, by the way, to be older than 200 million years, because even though ocean floor is created at a ridge because of seafloor spreading, before those rocks would get to their 200 million year old birthday, they would go down a trench, down a subduction zone, and get destroyed. Trenches and ridges, by the way, were basically discovered by geologists who were doing some work during World War II. And so trenches, are just these big, deep areas on the ocean floors. And now we know that they basically signal the process of subduction at a convergent plate boundary. Like ridges are basically long ridges of mountainous areas, and we now know that essentially what it is that there's magma pushing up on the edges of two plates, causing them to slightly rise on both sides, creating these ridge-type features. We have a ridge down through the middle of the Atlantic Ocean, and we have a ridge down through the middle of the Indian Ocean. So now we're going to talk about the different types of plate boundaries, and the first type of plate boundary that I'm going to talk about is a divergent. So divergent is when two plates come apart. So the magma moves up and basically pushes up on the edges of the two plates, and the convection currents go out in opposite directions, taking one plate one way and the other plate the other way. And that's going to create a gap, and that's where your volcanoes are, and where lava pours out onto the floor and creates these new rocks at these ridges. And this is what we call a seafloor spreading. Naturally, the convection currents are going away from each other, so that basically is exerting tensional stress on this type of environment, which we're talking about, which is a divergent plate boundary. If you look on this map, some places they're called ridges, some places they're called rises, but this is just to quickly show you where we have them on our planet. So you can actually see over here we have a ridge in the middle of the Indian Ocean. We have a ridge here going up through, which is the Red Sea. We have one that's coming all the way down through the Atlantic Ocean that includes Iceland and Surtsey, which are little islands here. We have a little ridge below, basically between Australia and Antarctica. So they're mostly where we find our ridges. Here's kind of a cool map because this is kind of showing the ocean floor of the Pacific, and you can actually see the real deep areas where the trenches are. So you can see like a trench here and a trench here. This is the Japan Trench, and then down here we have the Philippines, which is the Marianas Trench, and we have all the trenches here all up along the side, Alaska, and down here. So that these are all trenches. That's where subduction is taking place. That's where convergent plate boundaries are. But this right here is a little different. As you can see here, this is a ridge system. So this is where one plate is going one way and one plate is going the other way, and we have a process called seafloor spreading. It's kind of cool to look at a map of the ocean floor and what you actually can see. So this basically just shows you a ridge at a divergent plate boundary, which we just talked about. The second type of plate boundary is a convergent plate boundary. Now, the only thing I will say with a convergent plate boundary is that there's three types. So you can have an ocean colliding with an ocean, like Japan, the Aleutian Islands, and the Philippines, or you can have an ocean collide with a continent, like we have in the Rocky Mountains and the Andes Mountains, or you could have a CC, which is a continent colliding with a continent, which is what we have in the Himalayas, with India colliding into Asia. The thing that is common to all three is that one plate will subduct down underneath the overriding plate, and that will always create a trench, which you can see right here, and it will also create, and you will also have compressional forces because the two are coming together. So compression, trenches, and subduction all go together with convergent plate boundaries, and naturally it's all caused by convection currents. So the convection currents have to be bringing the plates towards each other. So this is Harry Hess's idea, and so basically Hess and Deitz, their idea basically extends in this area where one convection current goes one way, one convection current goes the other way, creates a hole, and then lava basically pours out on the ocean floor, creating new ocean floor. So we have a process called seafloor spreading. Over here is where rocks are getting destroyed, so convection currents are bringing them towards each other, and one goes down and gets subducted and gets destroyed. And we have a trench in that area as well. You can also see big volcanoes in this area. These would be more composite volcanoes due to the presence of a felsic continent, whereas here these volcanoes along the ridge would be mostly shield volcanoes because there's no continent involved, so it's just low silica mafic rocks. So here we can see we have an ocean colliding with an ocean, so that would be an ocean-ocean convergent plate boundary. Same here with Japan, same here with the Philippines. You can see the trench with the deep water. We have subduction and stuff going on. And we also have the same thing over here, but this is an OC collision. So Alaska and like British Columbia, we have an ocean plate subducting underneath a continental plate. That's essentially it in this particular diagram. There are hot spots. Like Hawaii, which we'll talk about later. But for now, typically this whole slide is just about trenches and subduction. So why is the Earth not getting any bigger? Well, because we have ridge volcanism at divergent plate boundaries that's creating new crusts, and we also have subduction zones and trenches at convergent plate boundaries where rocks are actually getting destroyed. So we're getting the recycling of crust. The third type of plate boundary is a transform plate boundary, which is discovered by J. Tuzo Wilson, and is when two plates basically grind past each other in opposite directions. There's no rock created, there's no rock destroyed. Sometimes you get a little bit of friction and pressure and stuff due to the rocks grinding past each other, and you get some low-grade metamorphism, but that's essentially it. So no volcanoes, just earthquakes. San Andreas in California and the Alpine Fault in New Zealand would be the two best examples. In this particular case down here, if you were to look at this little, I guess you could call it the sedimentary layer, and this little sedimentary layer, they don't line up anymore. The arrows on this diagram are wrong. This plate should be going this way, and this plate should be going this way. So they're sliding past each other, but this looks like a left lateral transform plate boundary to me, because if I stood on one block and looked over at the other block in this case is going to the left. So in this particular case here, we have a divergent plate boundary because that plate is going to the left and that plate is going to the right. This is a ridge where seafloor spreading takes place. The same thing applies to here. However, in this little place here where we have the big bolded circle, because this plate is going to the left, then right here it's going to the left. Because this plate is going to the right, then right here it's going to the right. So in this little tiny area here, the two plates are actually sliding past each other. So that is a transform fault, and that was discovered by J. Tuzo Wilson.